So, today we are going to start some new topics. So, they are listed here. First, we will look into how to define velocity and acceleration for a deformable body. Then we will look into a very important concept of material time derivative. Finally, we will see there is a relation between directional derivative and the material time derivative. Okay. So, we will look into this important connection, and towards the end we will look into the concepts of velocity gradient tensor, rate of deformation tensor and the spin tensor. Okay. So, let us start. So, many nonlinear problems you would know are time dependent. Okay. So, static problems are just a idealization of dynamic problem. All problems are dynamic. It is only when the inertia effects can be neglected, then we get the static problem. But there are certain problems like crash, okay, impact and all these kind of problems where time effect cannot be taken out. Okay. In that case, we have to consider velocity and material time derivative of various quantities. Okay. So, even though a process may not be time dependent, okay, it is nevertheless convenient to establish equilibrium equation in terms of virtual velocities. That is what we are going to do later on when we are going to derive the virtual work. Okay. We are going to use virtual work. So, there instead of virtual displacement we are going to use virtual velocities. Okay. So, equilibrium equations need to be established in terms of virtual velocities and their associated virtual time dependent quantities. Okay. So, for this purpose, now consider the motion of the body which is given by x equal to psi, okay, and psi is a function of the material coordinates x and current time t. So, what this tells you is the current location of a material particle which was originally at coordinate capital X. Okay. So, now the velocity of the particle is now defined as the time derivative of psi, okay, and the velocity is written as v equal to del psi by del t for a fixed material particle. Okay. So, this definition, okay, gives you the velocity of a particular material particle x at time t. Okay. So, during the deformation the particle is moving over space. Okay. So, as this changes its position in space, how does its velocity change? Okay. So, this relation gives you that particular information. Okay. So, this velocity is also written as del x by del t or equivalently as x dot. Okay. And in some books you will also find dx by dt. Okay. You will find dx by dt. Capital D actually is used for derivative, time derivative, where x is fixed, the material coordinate is fixed. Okay. So, equation 79 gives you the velocity at time t of a particle which was originally located at material coordinate x. Okay. So, this will always give you the velocity of a particular particle. Okay. Now, you note that velocity is a spatial vector. Okay. It is not a material vector, even though you see there is a material coordinates, but it tells you that velocity is a spatial vector despite the fact that the equation has been expressed in terms of material coordinates of the particle, okay, that is capital X. Okay. You can always invert this relation over here. You can always get X as psi inverse X comma t. Okay. And then you can substitute for this capital X in equation number 79 to get velocity v as psi inverse x comma t. Okay. So, this is velocity at the spatial position x. Okay. Now, moving on to acceleration. So, acceleration is now defined as the double derivative of the motion psi, okay, and it is given by a, okay, equal to del square x by del t square or equal to x double dot. Okay. So, this equation number 80 gives you the current acceleration of a material particle which was located at material coordinate x. Okay. So, with this, now let us take one example. Okay. So, consider the motion. Okay. Remember, now we have a time dependent motion. So, time now comes into the picture. So, some of the previous examples that we did, there was no component of time, there was no t involved, but here in this motion you see the spatial coordinates are related to their material counterparts, okay, and also there is a factor of time. Okay. Now, you have been asked to determine the velocity and acceleration. Okay. So, velocity is nothing but del x by del t, and acceleration is nothing but del square x by del t square, and both of these have to be computed for fixed value of x, which means you have to keep the material coordinates x1, x2, x3 fixed during the differentiation. Okay. So, V1, what will be V1? V1 will be del x1 by del t. Okay. So, from first relation, if you take del x1 by del t, you will get material coordinate capital X1. Then V2 will be del x2 by del t. Okay. So, you will get twice of 1 plus t material coordinate x2. Okay. Similarly, the third component of the velocity V3 will be del x3 by del t, which is equal to 2t times material coordinate x3. Okay. So, these are the, so you will see you have material coordinates on the right hand side, which means these correspond to the current velocity of the material particle which was originally located at x. Okay. Now, let us see how to compute the acceleration. Acceleration, you can take the time derivative of velocity, or you can take double time derivative of the motion itself. Okay. So, this can also be del v by del t, but remember here it has to be in terms of material coordinates. Okay. So, if you do this, you will get a1 equal to 0, because you see there is no time derivative, I mean there is no time component here. A2, the second component will be twice of x2, and third component of acceleration will be twice of x3. Okay. So, in this way you can get the acceleration and velocity of a material particle, okay, x at time t. Okay. So, you can get the current position of that material particle by this equation of motion, okay, and you can get its velocity and acceleration by taking the derivative of the motion with respect to time, keeping the material coordinate x fixed. Okay. With this, we now move to our very important topic of material time derivative. So, when a physical quantity, okay, so any physical quantity, for example, scalar or a tensor like temperature, velocity, stress, okay, when they are expressed in terms of material coordinates, okay, x, that is g equal to x comma t, okay. So, g can be scalar, g can be vector, g can be tensor, okay, or any other higher order tensor, then the time derivative of this physical quantity g is written as g dot is equal to del g by del t, or I said in the previous slide that material time derivative is conventionally in many books you will find they also use this capital D. So, del g by del t, okay, dg by dt equal to del g by del t. Okay. So, this is for fixed value of material coordinate. Okay. So, if you are given a physical quantity in terms of material coordinates and time, it is very easy to compute the time derivative, because the material coordinates are fixed, you know their location. So, it is fixed, it will not going to change over time. Okay. So, this expression what it does is it measures the change in the physical quantity g associated with the fixed particle which is initially located at material coordinate x. Okay. Now, this equation number 81 is called the material time derivative of the physical quantity g. Now, what happens? There are spatial quantities which are expressed in terms of spatial coordinates x. Okay. Now, you know as a motion progresses, the spatial coordinate of a material particle x changes over time. Okay. So, then finding the material time derivative of the spatial quantities expressed in terms of spatial coordinates becomes complicated. Why? If you have g in terms of spatial coordinate x and you have in terms of time. Now, if you have to take the derivative of that spatial quantity in terms of time, then not only the time changes, but also the spatial coordinate x is changing with time. Okay. So, in our previous expressions, the material coordinates x here, they were not changing with time. Okay. You knew their position, okay, initial position. So, they were not changing with time. What it means is, now we have to carry out material time derivative of physical quantities g which are expressed in terms of spatial coordinates a little differently. Okay. And this you can carry out using equation number 82. So, I am not going into the derivation of it, okay. You can see from any textbook how to carry out these kind of differentiation. So, what this means is you have been given a physical quantity g in terms of its spatial coordinates x and time t. This spatial coordinate x itself, okay, you would see is a function of time. Okay. It is a function of material coordinates and it is a function of time. So, now to take the material time derivative of this spatial quantity g, okay, this is del g by del dg by dt, you can do by taking del g by del t. So, which means you keep the spatial coordinate fixed plus what is called a convective term, which is taking the gradient of the physical quantity times the derivative of the motion with respect to the time. Okay. So, in short I can write the material derivative, time derivative of a spatial quantity g is nothing but the derivative of the spatial quantity with respect to time, keeping the spatial coordinate fixed, plus the gradient of g times the velocity. You can recognize that this is nothing but velocity, okay, because it is here that x is fixed, okay, the material coordinates are fixed. So, this equation, okay, I am reproducing here again. So, it has two terms. Okay. So, the material time derivative of a spatial quantity has two terms. Okay. You can see this is the first term and this is the, so this is the first term, okay, and this is the second term. Okay. So, the first term is what is called the local rate of change, okay, is the rate of change of the physical quantity currently at x. Okay. So, locally how it is changing. Now, the second term is called the convective term, because it is like a term which is convecting with the spatial quantity. Okay. Now, let us see, to clarify this further, let us see one example. Okay. So, this specific example you see here, you consider a velocity meter to measure velocity at a position x of a fluid flowing through a channel. Okay. So, this blue box that you are seeing is a channel, okay, and let us see, this blue thing that is there is the fluid which is flowing through this channel. Okay. And let us fix our coordinate system. Okay. Then, to measure the velocity of the fluid which is flowing through this channel, what you have to do? You have to put some velocity meter. Velocity meters are instruments that are used to measure velocity. Okay. So, let us say you wanted to measure the fluid velocity at position A, whose coordinate, okay, is given by x a. Okay. So, let us see, this is your velocity meter, okay. And now, somebody asks you, what is the acceleration of the material particle which is currently passing through position A. Okay. So, I am not saying what is the acceleration at position A. What I am saying is, how do you find acceleration of a material particle which is currently passing A. Okay. So, it is a little different. I am not fixing the position x, but I am asking about the particle which is passing currently at x, which is currently there at x. Okay. So, now the velocity meter that you have, okay, the velocity meter that you have here will measure the local velocity. Okay. This velocity meter does not measure the velocity of the particle, it actually measures only the velocity at location A, okay, which means for a fixed spatial position x, it is measuring the velocity. Okay. So, at the time progresses, different particles will come and occupy that particular position A, and when you see that velocity meter readings, what you are seeing is basically velocity of different particles which are passing that position with time. Okay. But now, we are interested in the acceleration of the particle which is currently passing that location A. Okay. So, the acceleration which I have written here, now you have to, you only have the local information. Okay. So, g here, okay, x comma t for you here is your velocity, okay, x a comma t, let me write v a. Okay. So, you only have the local measure of velocity. Okay. Now, from this you want to find out the acceleration of the particle at A. Now, this local information, okay, is velocity, and then to find the acceleration of the particle that is passing at A, we have to take the local rate of change of velocity, okay, plus the gradient of the velocity at A times the velocity at A. Okay. So, the local rate of change of the velocity can be obtained by this velocity meter. Okay. It is always possible. Okay. In real life application, you can say, after say you want to find out the rate of change of velocity. So, say you fix 1 second as your delta t. So, you see how much the velocity at A has changed, that will give you approximation of the rate of change. Okay. So, you see the velocity meter, you note the reading at t1, and then after delta t you remeasure the velocity, and then you get the velocity change, rate of change of velocity. Now, the problem occurs, and you also at time t will know the velocity at A. Okay, that is the direct reading of the velocity meter. The problem is how to find out the gradient of the velocity. Now, to find out the gradient of the velocity, okay, you can fix another velocity meter at position B, a little farther into the stream, let its position be xp. Okay. And then you can approximate the velocity gradient at A as the difference in the velocity measurement of the two velocity meters divided by the difference of the positions. Okay. So, this is nothing but delta v by delta x. Okay. Now, the closer you put this velocity meter to position A, the more accurate you can get the measure of the gradient of the velocity. Now, if you have these quantities, you can compute the acceleration of the particle that is passing current position A. Okay. So, what equation 83 okay, shows, and this example shows that it is perfectly possible to compute the material time derivative using only the current information, okay, information at the current location, okay, which is in terms of spatial position x and time t. Okay. So, this expression helps you to find out the material time derivative of a spatial quantity using only the spatial information. Okay. So, you can get the material information, okay, using the spatial information. Okay. Now, let us see one example. We take example number 4 and we invert the motion. Okay. So, we had that motion, okay, spatial position in terms of material position and time. Now, what we do? We write the material position in terms of the spatial and the spatial position and the time. And now, we wish to determine the acceleration. Okay. Now, previously in example 4, acceleration was directly obtained because the material coordinate x was fixed. Now, we have been given the information in terms of spatial position and we want to find out the acceleration. Okay. So, we can write acceleration as the local rate of change of velocity plus the gradient of velocity times the velocity itself. Okay. Now, the velocity we have found out in an example number 4 as v1 is equal to x1, v2 equal to 2 1 plus t x2 and v3 is 2t x3. Now, we can substitute for x1, x2 and x3 from our motion here. Okay. We can substitute from our motion and then we can get the velocities. Okay. So, once we do this, we can get our velocities in terms of the spatial coordinates. Okay. So, that is the velocity that we have in terms of spatial coordinates. And now, so you see here we have to have the velocity in terms of spatial coordinates and these are the velocity in terms of spatial coordinate. Okay. Now, the gradient of velocity, which means del v by del x, you can compute. Okay. So, del v by del x you can compute, and because v1 only depends on x1, v2 only depends on x2, v3 only depends on x3, we get del v1 by del x1 as 1 upon 1 plus t, del v2 by del x2 will be 2 up by 1 plus t, and del v3 by del x3 will be 2t by 1 plus t square. Okay. So, now we have the velocity, we have the gradient of the velocity, and now we can compute the first component of the acceleration as v1 dot. Okay. So, this vector equation we can write in component form. So, the first equation will be a1 equal to v1 dot plus the first component of the gradient times v1. Okay. This actually will be a del v1 v1 plus del v2 plus del v3 but because the other two terms are 0, we only have del v1 into v1. Okay. You can take the derivative of this quantity with respect to time. Okay. So, it will be minus x1 upon 1 plus t the whole square, and the first component del v1, the first component of the gradient is 1 upon 1 plus t. Okay. So, that is 1 upon 1 plus t, and this is the first component of the velocity. Okay. And when you simplify this, you will get 0. Okay. So, you remember our acceleration when we computed in example 4 was also the first component was equal to 0. Similarly, I leave it to you to compute the other components of the acceleration. Okay. So, a2 will be v2 dot del v second component into v2, and everything is known, you substitute and you will get 2x2 by 1 plus t the whole square. Similarly, the third component you will get, okay, sorry, this is a3, the third component will be 2x3 upon 1 plus t square. Okay. Now, what you can do, check whether this solution is correct. What you can do, these spatial position x2, x3 you can write in terms of material positions capital X1, capital X2, capital X3 in terms of this motion. Okay. So, this motion is given to you. So, if you substitute this here in this expression, you will get a1 as 0, a2 as 2x2 and a2 as 2x3, which is exactly what we obtained in example number 4. Okay. So, you see this expression for the material time derivative and one which was originally there are one and the same. In the first case, what we discussed, the spatial quantity or the physical quantity was given in terms of material coordinates and time t, and in the second case the physical quantity was given in terms of spatial coordinates and time t. Okay. And then to find out the material time derivative, you have to see whether your physical quantity is given in terms of material coordinates or spatial coordinates. If it is given in terms of material coordinate, you just simply take derivative with respect to time. If the physical quantity is given in terms of spatial coordinates, then you have to use this particular expression. Okay. Okay. So, this particular expression you have to apply and you have to get the material time derivative. Okay. Now, there is a definite relation which exists between the directional derivative and the material time derivative. Okay. So, consider you have a general operator f that applies to the motion, okay, given by x equal to psi of x comma t. So, you can show, and this proof I am not doing in this particular course because it is not part of this applied course. You can show that the directional derivative of that general operator f in the direction v is same as the material time derivative of the general operator f. Okay. So, which means that the directional derivative of f in the direction v is same as the material time derivative of f. Okay. So, we will take show this using one example which we take as the material time derivative of the deformation gradient tensor f. Okay. So, the material time derivative of f is f dot, which is nothing but d by dt of del psi by del x. Okay. F is nothing but del psi by del x. Okay. Now, I can move del psi by del x outside the bracket and I can move d by dt inside. Okay. So, I can rewrite this expression as del by del x into del psi by del t. Okay. And now, psi is given in terms of material coordinates. So, I can directly take its time derivative, and this is nothing but your velocity v. Okay. And del by del x is nothing but del 0. Okay. So, the deformation gradient tensor f, which is given by f dot, is nothing but del 0 v, or the gradient of velocity with respect to material coordinates. Now, let us see the other way around. We have derived, okay, in our previous lectures, the directional derivative of the deformation gradient tensor in the direction of displacement u, okay, and it was given by directional derivative of f in the direction u is nothing but the gradient of u, okay, with respect to the material coordinate del 0 u. Now, I can take the directional derivative of the deformation gradient tensor. Instead of taking in the direction of u, I can also take in the direction of velocity, because velocity is also a vector, u was also a vector. So, instead of u, now if I take in terms of velocity, what do I get? I can simply replace u by v, and then the directional derivative of f in the direction of velocity will be nothing but gradient of velocity with respect to material coordinates, and this from equation 85 you can see is nothing but f dot. Okay. So, what we have shown here is that the directional derivative of an operator f, here the deformation gradient tensor taken in the direction of velocity is nothing but the material time derivative of that operator, here deformation gradient tensor. Okay. So, next we move to our next topic.